About joint work on spectral analysis of matrix scaling with Chiu, Kwok, and Lapchila.
So yeah, thanks for the introduction. My name's Akshay, and this is joint work with Chiu, who's at Shanghai University, and Lapchila is my advisor, who's also at Waterloo. And we'll be talking about spectral analysis of the matrix and operator scaling framework that we have seen before in a couple of talks yesterday. So the plan is, I'll first define the two problems, what is matrix scaling and what is operator scaling. Then I'll define this continuous process that we analyze using a spectral condition, so in a special case. And then I'll give some nice applications of this kind of analysis that tends to bypass some technical details in previous works. I know it says proofs. There's a slide on proofs, but I probably won't get to it, or it won't be that detailed. So feel free to come talk to me after. So what is the matrix scaling problem? We're given a non-negative m by n matrix B, and we'd like to scale it using diagonal matrices on the left and right to make all the row sums and all the column sums the same. For illustration and for the rest of the talk, it's good to think about just the n by n case. And so here we want to scale the rows and columns to make it doubly stochastic, right? There's another interpretation as this singular vector type problem. So notice that a doubly stochastic matrix has the all ones vectors as singular vectors. So we'd like to scale our matrix to make these the right singular vectors. And also there's a combinatorial interpretation. So B represents the adjacency matrix of a bipartite graph, right? If there's an entry in ij, that's the weight of the edge between the I on the left side and the j on the right side. And so there's some flow interpretation here, which should remind you of Hall's theorem and flow problems. So let's quickly do an example. So this is our simple 2x2 matrix. It's not clear to me how to look at this and tell whether it's scalable or what the answer is, but here is the answer. And you can check this, that you come out with a doubly stochastic matrix at the end. So again, it's not really clear whether this matrix is scalable, which is kind of the question we're trying to answer. But there is some natural first steps that we could take. We want to simultaneously satisfy a row condition and a column condition. So let's iterate back and forth, right? We can satisfy the row condition and then satisfy the column condition. So first we'd scale all the entries by the row. So we scale each entry by its row sum. And then we'd scale each entry by its column sum. And then we iterate repeatedly. And hopefully we'd end up at a scaled input. So we'd like to analyze the convergence of this kind of algorithm. And in fact, this algorithm is used in practice to do matrix scaling in statistics and optimal transport and stuff. So this algorithm was analyzed. And it showed if you want an epsilon approximate answer to the condition, so you want to satisfy both the conditions up to this epsilon, you can do so in 1 over epsilon iterations. And this algorithm exactly was used to show a deterministic, strongly polynomial time algorithm for matrix scaling and approximating the permanent in LSW. As I mentioned, there's this flow interpretation, so you believe that this has relations to counting matchings. The reason for this was, turns out that there's a sufficient condition for these problems which says I just need to scale to a inverse polynomial error, and then I can answer my decision question. And so since I have a polynomial in 1 over epsilon type of convergence, this is a polynomial time algorithm. So now we'll talk about the generalization to operator scaling. I will mention all of the definitions and analysis we do carry over to this setting, but you don't actually have to worry about it if you don't like the notation. All the ideas are well illustrated in the matrix setting, and you'll understand all of the analysis from just the matrix setting. But I will mention all the definitions in both. So what is the operator scaling problem? It turns out to be a generalization of the matrix scaling problem. You are given these tuple of matrices AI, and you'd like to satisfy these two simultaneous balance conditions. So AI star, you want that to add up to the identity, and then AI star AI. You want that to add up to the identity. And the operator scaling problem is just like the matrix scaling problem. I'm given these tuples, and I want to scale them simultaneously on the left and right, such that I satisfy these two balance conditions. Is there any questions about the problems? Cool. So again, there's a natural alternate scaling algorithm, which is sort of the first heuristic you try. And again, there's analysis that shows that this kind of algorithm converges in polynomial in 1 over epsilon time. So if I want an epsilon approximate satisfaction to both the balance conditions, I can do so in polynomial time. And so this framework came to our attention because of this recent work showing that this gives a deterministic polynomial time to this non-commutative variant of this thing called Edmonds problem. That's a typo. It's not a special case of PIT. It is a non-commutative variant of PIT. But this was shown in the recent operator scaling works in 2016. So now we've defined the problems. I'll mention that this kind of problem has shown up in lots of communities in lots of different settings. So in particular, matrix scaling is already useful for statistics and optimal transport, and as I mentioned already, the permanence. Frame scaling is actually our motivation. So this Paulsen problem at the bottom was how we saw this framework, and there's some other applications as well in TCS. And finally, the operator scaling, most general operator scaling setting has been used recently to do a lot of nice algebraic work. I'll call your attention to the bottom point, orbit intersection. So as I mentioned before, the non-commutative Edmonds problem and the permanent problem, all you needed was inverse polynomial error. So a polynomial in epsilon time algorithm is fine. For the orbit intersection problem, you actually needed inverse exponential error. And so they had to use some new second order tools and continuous optimization to solve this problem. But our analysis will have something to do with this kind of exponential convergence as well. And I'd like to mention our spectral definition gives improved bounds in the Paulsen problem, which I'll mention, and in permanence for certain matrices. So in certain special cases, we get improved bounds for these two problems. So now I'd like to define the continuous scaling problem. The continuous scaling process, I will mention, like just to keep it in the back of your head, the Paulsen problem is a question about bounding the distance between the input and output. So this continuous scaling helps do that better than the alternate scaling. You sort of jump too far to give good bounds in the alternating algorithm. So what is the continuous process in matrix scaling? We'd like to fix two balance conditions. So we'll do them simultaneously and infinitesimally. So I'll walk through this a little slow. Remember, in the alternating algorithm, if one row was too big, we divided by the row sum. And if a column was too big, we divided by the column sum. Here, notice the first term, if a row is too big, S is the total sum of all the rows. If a row is too big, then we're pulling it back towards the average, but infinitesimally, so we make it smaller. And simultaneously, similarly, if the column is too big, we pull it back towards the average. So you believe that at the end of this process, it converges to doubly balanced. Again, there is a definition in the operator case. It's not too much to look at. This is sort of the first generalization you could think of. It's just two balance conditions. You're satisfying them both infinitesimally and simultaneously. Cool. So we came across this continuous process when we were studying the Paulsen problem, in which we wanted to bound the distance between our given input and the scaled output. So you'd believe that as you watch this process go, you can bound, for example, speed of convergence and as well speed of movement to bound the total distance that you moved. There's actually another really nice interpretation of this process, and it's come up in various communities before. So this is a natural error measure to test how close I am to doubly balanced, right? I would like all of my row sums to be the same and all of my column sums to be the same. So I can measure the L2 error of this measure. And so this delta is a nice error measure to look at. And turns out that the continuous process we defined before is exactly a gradient flow of this delta. So if you take the gradient with respect to the matrix entries of this measure, then you get naturally the gradient flow. I'll mention that this was studied independently and much before us in a much more general setting in symplectic geometry by Kirwan. So we didn't invent this, but it turned out to be really natural and useful for our problem. Again, this is the delta definition for the operator setting. And again, if you take a gradient flow with respect to this delta, you get the continuous process. It's not super clear. Like, it is some calculus you can do on paper, but it's not super clear right away. Cool. So now that we've mentioned what the continuous process is, we'll analyze it in a special case where we get much faster convergence of our process. So we'd like to define the spectral condition. So recall we have a matrix, and the spectral condition will be that the matrix has a spectral gap. So remember, there is a singular value interpretation of this matrix scaling problem. So I want my top singular value to be 1. I'm asking for the spectral condition that all the other singular values are far away from 1. This can be interpreted in an optimization perspective as something to do with strong convexity, but I won't really talk about that too much. I'll mention one optimization application later. There's another combinatorial interpretation, which is nice. So recall that B is the adjacency matrix of a bipartite graph. Then if that matrix has a spectral gap, then you can imagine the graph underlying is an expander. So we're talking about certain better bounds if your graph is an expander. And another natural reason for this definition is, turns out certain random distributions of matrices satisfy the spectral condition with constant spectral gap. So this gives evidence that this might be a good way to analyze these problems. Again, in the general operator setting, there's a derived matrix from our tuple of operators, and if this matrix has a spectral gap, then we get better convergence. So we want the second singular value of this matrix to be far away from 1. This was actually already studied in quantum information theory. It's known as quantum expanders, a slightly variant notion of quantum expanders. And again, there are certain distributions. I think random unitaries are a good distribution. So if you take random unitaries as your tuple, they satisfy this strong spectral gap condition. Cool. So what is our main theorem in this setting? So let's say that you're given a tuple of matrices that is epsilon almost satisfying both the balance conditions, and it has a spectral gap that is large as compared to the epsilon approximation. Then we get linear convergence of our error measure. So exponentially fast, our error measure will decrease to 0. In particular, what's nice was we were able to get algorithms for certain decision problems based on sufficient conditions for scalability. If I can scale to this error, then I know that it's scalable. This actually gives new sufficient conditions for scalability, which were not covered by the previous sufficient conditions. In a special case, you do need spectral gap. So as a byproduct of our analysis, we were actually able to show certain bounds on this thing called the condition number. So I want to scale my input. I can measure how far I have to scale it by asking how far am I scaling it from the identity. So what is the maximum over minimum singular value of my scaling matrices? And we were able to give, in general, this condition number could be exponential in MNN, even for scalable inputs. So it's not really clear how small this could be. But in our special case, this is a really small constant. So if you look at the parameters from last time, lambda was bigger than epsilon over epsilon times log n. This is just a small constant. This has an optimization perspective. Turns out this quantity was used to give running time bounds for certain second order methods. And so our analysis shows these kind of algorithms are in fact near linear time in this spectral expansion case. Cool. So we've talked about the spectral condition itself. I'll give a couple of motivating applications, in fact, why we thought of this definition. So we were studying the Paulsen problem earlier. Paulsen problem is concerned with frames. So you're given a set of vectors, and you want them to add up to the identity in the outer products. So you want them to be balanced around. You can think of this as a coding problem. So a basis gives you a way to code a vector in the vector space. So does this set of vectors. You could take the inner products and send the coefficients to someone else. That's your code. So in Holmes and Paulsen in 2004, it was studied these kind of frames that are robust to erasures. So it turns out if you want to be optimally robust to dropping one of the coefficients, then you'd want all the vector lengths to be the same, right? That sort of means they're all equally important in the code, and so if you drop one, it's fine. So this kind of problem will be called a Paulsen type problem. And then they had a further motivation, which was if you want to be optimally robust to 2 erasures, that you need all the vector lengths to be the same, and you want to minimize the angles between the vectors. So you want them to be very well balanced. This has applications as well in quantum information theory. We'll call these Grassmannian frames. So the first one was Paulsen frames, where all the vector lengths are the same, and the second one is Grassmannian frames. And turns out our analysis gives improved, beyond worst case analysis of the Paulsen bound that we showed earlier, and it gives really easy new constructions of approximately optimal Grassmannian frames. So if these problems occur, we'll move on to the idea from Holmes and Paulsen. So we want to construct explicit constructions of Grassmannian frames. There are really specific constructions that require algebraic definitions, and they sort of even depend on like the number of vectors versus the dimension. They only exist in some dimensions. So if you want optimal Grassmannian frames, it's sort of hard to construct explicitly. So we can imagine a numerical relaxation. You generate some sort of approximate satisfying those 2 conditions, and you try to move to an exact solution, or at worst, even just certify that your solution is close to an exact solution if it was approximately close to start with. And so this motivates 2 natural questions, one related to Paulsen and one related to Grassmannian frames, of how well does this work, right? So we'll talk about how our analysis gives beyond worst case analysis of these kind of. This Paulsen problem is just a formalization of the first question I asked. So how well does this rounding work? If I was given a bunch of vectors that approximately satisfied both the 2 conditions, I want to find nearby vectors that exactly satisfy those 2 conditions, and I want to bound how far I have to move between these 2 vectors. I'd like to give a bound in terms of the number of vectors n, the dimension d, and the original approximation error epsilon. And in fact, the main conjecture was that this bound should not depend on the number of vectors. right? You'd believe as the number of vectors grows, each vector gets smaller, so you can bound the total distance without calling upon n. So in a previous result, we were able to show this. We were able to remove the n dependency. And in fact, this is where we first saw the continuous scaling process. I'll mention in an unrelated set of techniques, Hamilton and Moitra showed a much stronger bound, d squared epsilon, with like a really simple proof. It's a really beautiful paper. The proof overall takes like 3 pages. It's just a clever way of using distance measures to do this problem. And in fact, this bound that Hamilton and Moitra gave is tight up to an extra d factor. There's really simple perturbations of type frames that require d epsilon. So we're almost closing this gap. But what did the spectral analysis give us? It gave us beyond worst case analysis of this kind of problem. So turns out this frame scaling problem is a special case of the operator scaling problem. And in this setting, the spectral gap is actually the spectral gap of this matrix of inner products squared, so the angles. And if this matrix has a spectral gap, then we were able to show the total movement is in fact d epsilon squared, so better than the worst case bound of d epsilon lower bound. Further, notice that if you take random unit vectors, the inner products, so what we just showed was a better worst case analysis for Paulsen problem. Now I'll move to our result for Grassmannian frames. Notice that if you take random unit vectors, then the average inner product is 1 over d, right? Which is optimal. You can't expect better than that. But with concentration, you could expect close to that, right? So it turns out that if we generate n large random unit vectors, not only do we get, with high probability, we get low angles altogether, but we also get a spectral gap. And so what our analysis was able to show is that there's really easy constructions for these almost optimal Grassmannian frames. So the natural process of generating a bunch of random unit vectors and then scaling them would show that you get almost optimal Grassmannian frames nearby from where you started. I'll quickly go over the last permanent application. So the permanent is, just think of this as a 0, 1 matrix, and this is counting the number of first matchings. The van der Waals theorem was a really nice theorem that showed for a doubly stochastic matrix, the permanent is between 1 and exponential in n. And this was used, as I mentioned before, in LSW to use scaling to give a deterministic exponential approximation to the permanent. So you first scale to doubly stochastic, and then you have this van der Waals theorem to show you're exponentially close to what the answer is. Turns out that our results can be used to prove a approximate van der Waals type theorem for non-doubly stochastic matrices. So if you satisfy the two you're approximately doubly stochastic and you have a spectral gap, then we can show that our permanent is only a polynomial factor off of this exponential bound. So this is I don't know that many results on non-doubly stochastic matrices for permanents. Yeah, I think I'll skip the proof. We'll go to the open questions. So there's 2 natural open questions you can ask in this framework. So the recent work has been done for much more general problems, tensor scaling and various different marginal type problems. They're sort of finicky with the relation to like algebraic conditions and rational representations of the desired marginals you want. This kind of analysis doesn't really care about that. So there's a hope that there might be a spectral analysis for these more general settings. I haven't defined these problems, but feel free to ask me after. So yeah, the first open question is whether there's spectral analysis of more general settings. And the second one is we've analyzed this continuous process, but you might believe that the discrete process is also an optimization method and so should also be able to be analyzed for fast convergence in the spectral setting. So can we do that? Cool, thank you.
Any questions for Akshay?
So it's not clear what the definition for tensors is.
Yeah, even for arithmetic. Okay, even in the case that we
Right. I'm not sure that if it converges fast, that means there's a spectral gap. I think there might be other cases where it still converges fast.
What does the lower bound for the permanent look like in lambda? Like what kind of?
I think we use lambda as a small constant. So lambda has to outweigh the approximation error. So it has to do with the ratio between epsilon and lambda.
For the lower bound, then?
Yeah, for the permanent lower bound, the approximate van der Waals type theorem. It has to do with the ratio between epsilon and lambda.
Other questions?